My name is Jim Cullafello, and I'm the Vice Dean of Academic and Student Affairs at the Ira Fulton Schools of Engineering at Arizona State University. It's my pleasure to welcome you to our National Academy of Engineering Grand Challenges for Engineering Speaker Series, hosted by ASU and sponsored by the Kern Entrepreneurial Engineering Network. This engaging speaker series will focus on the 14 Grand Challenges for Engineering in the 21st Century. Esteemed speakers from across the nation will be sharing their expertise on these grand challenges and answering your questions. We are proud to be a part of the NAE Grand Challenge Scholars Program, preparing graduates to address these challenges. It's my pleasure now to introduce Dr. Ramakrishna, the Director of the National Academy of Engineering Grand Challenge Scholars Program Network, to share his welcome.
Hello, my name is Ramakrishna and I am the Director of the National Academy of Engineering's Grand Challenges Scholars Program Network. The NAE Grand Challenges for Engineering, identified in 2008 by a committee of the National Academy of Engineering, are 14 critical global challenges for engineering in the 21st century, united by the mission of continuing life on the planet and making the world more sustainable, more healthy, more secure, and more joyful. The Grand Challenges Scholars Program, inspired by the NAE Grand Challenges, reflect the rapidly evolving nature of engineering education. The goal of the program is to prepare engineers who not only have the necessary technical skills, but also the cross-disciplinary knowledge, entrepreneurial spirit, the global multicultural perspective, and a sense of societal mission needed to meet the global grand challenges facing humankind in the 21st century. As of November 2018, 65 institutions across the US and around the world have implemented this innovative educational program, and nearly 100 are getting ready to join the consortium of GCSP schools. We at the National Academy of Engineering are thrilled that Arizona State University has taken the initiative to organize this series of presentations that will highlight each of the 14 NAE Grand Challenges and provide this valuable resource not only to its own students and faculty, but to students and faculty from around the world. On behalf of NAE, I'd like to thank ASU and the Kern Foundation for making the presentation series possible. I'm eagerly looking forward to following how this series impacts and inspires the next generation to create solutions to our society's most daunting problems. Our best wishes for a successful series, and thank you very much.
Trowbridge, and I'm the director of the Grand Challenges Scholars Program here at ASU. I will be the moderator of this first spring event of our Grand Challenges Speaker Series. I'd like to welcome you again and thank you all for being here. Tonight, Dr. Fran Ligler will speak about her path from research to products, including experiences related to the theme of health. Following her presentation, you'll have the opportunity to submit your questions, and I'll ask her your questions as well as a few of my own. There we go. I'm very excited to welcome and introduce Dr. Fran Ligler. Frances Ligler is the Lamp Distinguished Professor in the Joint Department of Biomedical Engineering in the College of Engineering at NC State University and School of Medicine at UNC Chapel Hill, and is an elected member of the U.S. National Academy of Engineering. Prior to moving to North Carolina in 2013, she was at the U.S. Naval Research Laboratory for 28 years, during the last 18 of which she was the Navy's senior scientist for biosensors and biomaterials. She earned a bachelor's degree from Furman University and both a Doctor of Philosophy and a Doctor of Science from Oxford University. Currently working in the fields of biosensors, tissue on a chip, and microfluidics, she has also performed research in biochemistry, immunology, and proteomics. She has over 400 full-length publications and 34 patents, which have led to 11 commercial biosensor products and has been cited over 18,000 times. She serves as an associate editor of analytical chemistry. She was elected an SPIE Fellow in 2000, a Fellow of AIMBE in 2011, a Fellow of AAAS in 2013, a fellow of the National Academy of Inventors in 2016, and an honorary member of the Hellenic Society for Nanotechnology and Health Sciences in 2017. In 2003, she was awarded the Homeland Security Award by the Christopher Columbus Foundation and the presidential rank of Distinguished Senior Professional by President Bush. In 2012, she was awarded the presidential rank of Meritorious Senior Professional by President Obama. In 2014 and 2018, she was awarded honorary doctorates from the Agricultural University of Athens, Greece, and Furman University. She is also a 2017 inductee of the U.S. National Inventors Hall of Fame, honored for her invention of portable optical biosensors. So please join me in welcoming Dr. Fran Ligler.
Thank you. It's really nice to be here, and I'm looking forward to your questions. I guess this format doesn't lend them to questions in the middle of my talk, but if you have a burning question, raise your hand and we'll try to deal with it. I don't have much time, so this is going to be a bit of a wandering talk, trying to focus on the relevance of healthcare and contributions to healthcare, but giving you an idea of how one person actually did it, as opposed to an ideal way of doing it. So I started out, I was born in Kentucky. I'm a fifth-generation Kentuckian. Daniel Boone's a relative. Abraham Lincoln's a relative. So I came from a very much a frontier-oriented family and spent most of my growing up wandering around the woods, either on foot or with my hound dog or on horseback. I still ride horses. I still climb mountains on horseback. So that's part of my genes. I went to Oxford for true love. My fiance won a Rhodes Scholarship. So if I wanted to get married, I had to go to Oxford. How's that for a reason to go to graduate school? After taking a degree in biochemistry and doing 1 year of biochemistry, I ended up going into immunology because it was his turn to move. I didn't realize it would take me a year to learn the vocabulary, but it did give me an appreciation for what it takes to jump from one field to another, and a realization that you can do it. It's not that hard. Once you learn how to learn, you can learn a new field, and that was a talent that will stand you in good stead for all of your life. When I got to I worked in the medical schools for 5 years, and then I went to DuPont and when I left there was head of cellular immunology. And I went to the Naval Research Lab because they were starting a group to build things from the molecular level up, like molecular tinker toys. I thought that was weird and would be fun, and I told them if I couldn't do it, fire me after a year. Obviously that didn't happen. But what I did discover was that I like to make things. I've always made things my whole life to solve problems, but now I had really big problems. I got there and I started thinking about problems beyond just medical ones and what kind of problems I had the skills to address. I also learned about the threat of biological warfare attack, which is very real, and that used to keep me up at night. I was one of the very few people that seemed to be worrying about it at the time. But I realized that I can envision a way of detecting biological warfare agents as they came through the air. I had a vision. I worried about the problem. I had a passion for solving it. And I created, with some of my colleagues to tell me what made sense and what didn't, a vision of what we could create to solve the problem. And that's how I got into the biosensor field, and B, realized I had to learn engineering if I was going to have any impact at all. So the way I learned engineering, unfortunately, was not to go to school. That's a much easier way to do it. I hired postdocs to teach me engineering. I hired an electrical engineer. I hired a chemical engineer. I hired a mechanical engineer. Anybody I could think of to bring into my group. I could teach them about biochemistry, but they had to teach me engineering because I had to understand what I could do and better yet, what I couldn't do. So I think it's really fun. Now I'm a professor of engineering and I've still never taken an engineering course. Right? So in terms of developing a product And in this case, we're talking mainly about biosensors, but for a variety of applications. What drives the work? It's really an awareness of what the problem is. And if you're going to create a solution to that problem, because that's what engineers do, we create things that don't exist. If you're going to solve a real world problem, you have to know what the problem is. So these are some of the problems that concern us. They're some of the problems we see the effects, negative effects around us. But what we forget is the user drives the system design. If we can think of a way to solve a problem, that's fine, but we also have to understand what the user is capable of in terms of using the solution, and what information are we going to provide and what they're going to do with it. There is no reason whatsoever to provide a person with a lot of information that they can't use to make decisions. So that's something to always keep in mind. We also have to keep in mind that somebody has to pay for the costs of products. Somebody has to pay for the work to make a lot of money, but I have to eat, right? And so does my group. We're an impatient generation. It's not, we want the answers now. So what kind of answers do we really need? If we don't need quantitation, then why provide it? If all we need is yes, no, something's there, something's not there, that's fine. But if that's not enough, we have to build in the ability to quantitate something. If you can't measure it, it's not real in terms of the thinking of the user. Where is it going to be used? So in this case, a biosensor would have to have a footprint that was appropriate for the place it's being used. If someone in the military is going to carry it around in their backpack, it can't weigh 50 pounds. If they're going to, I've actually designed, had some of my biosensors tested by people who are jumping out of airplanes or swimming underwater. You know, you have to be able to plan for things like that. That's getting easier than it used to be. Some of the other problems are also point us towards low-tech solutions. If we want a biosensor for food safety so that we're not poisoning ourselves with old food, we have to have a very low-tech solution with a very easy readout system and very easy for a typical consumer to use. So understanding the user is the key to making good choices. You want the lowest cost solution, the least technically, apparently technically simple solution. So if you look at if you have an Apple Watch and you look at it, it seems relatively simple, but you know that there's a lot of very high-tech development that went into that watch. It takes a lot, it's often very difficult to make something very simple, but in the end, that's what you want. In terms of devices such as biosensors that give us answers, you also need to know what the tolerance of the user is for false negatives and false positives. If I am developing a sensor for a biological warfare agent, and I know this from talking to the users, they don't want any false positives. It means that the military has to put on the heavy protective garment. It degrades their ability to perform, and they're incredibly hot. You'll hear some of that from first responders as well. So if you have too many false positives, say more than once a year, they simply toss it off the back of the truck. That's the fate of your biosensor. And I've seen that happen too. If you're going to make a sensor for a clinical diagnostic, you have to know what the regulatory hurdles are. Or environmental diagnostics, you have to know what the EPA demands for the performance of that device. And that has to be built into the design of the device that you're making. And the last one on here is freedom to operate. somebody's going to have to produce this device. Somebody's going to sell it if it's going to get into the hands of the users. There's several steps to that, and we'll talk about it a little more in terms of development of intellectual property. But it's not just how good your patent is. You also have to think about all of the other patents that play a part in the final product. And will the user or whoever's producing this have the freedom to actually manufacture it without licensing somebody else's technology as well as your own? So these are all sensors that have been produced commercially from the patents that I developed at the Naval Research Lab along with my team. The ones that are still available commercially. Our first experience with automation was putting a biosensor for BW agents on a drone. We did that in 1996. So think about what you knew about drones in 1996. Assuming you were born in 1996, right? And flew it out in the desert, and we proved that we could collect bacteria from the air, identify it, and radio it to the ground before it hit the people on the ground. Interestingly, one of the main problems we had to solve in putting the system in the drone is right here, this little tube coming out the front. Nobody had made a collector. We had a power budget that gave us about the amount of power that would power a light bulb to make this system. So we couldn't put a fan or anything in the collector. So what we did was we went down to our local hardware store and we bought a tube and made a little cone that would set up a wetted wall cyclone in there. The first time we did it, we had the tube under the wing, nothing happened. We moved the tube out to the nose, tried it out in the wind tunnel, and it worked just fine. So we could collect the bacteria, they'd run down the sides of the cyclone, and we could analyze it and radio the data back to the ground in under 10 minutes. That led to, these two devices here. This was for doing food testing, water testing, not only for biological warfare agents, but for bacteria and toxins and all kinds of other materials. This one has the air sampler integrated into it and tests for 8 different biological agents at a time, and the military can carry it on their back. These two systems were for testing for environmental pollutants. They, in under a minute, collect or test water samples, sample after sample after sample, and detect a small molecule if it's present. This one was commercialized for drugs of abuse in saliva, and instead of building a system, they wanted to do it on the cheap, so they just stuck it in the empty space in their computer. You can get some idea how old that was by what the computer looks like. But that was actually used in portals going into nuclear power stations to make sure people coming into work hadn't been on drugs or hadn't been partying too hard with alcohol, among other places. The president of the company that commercialized that system claimed he was going to test all his daughter's dates, but I never did ask him if he really did. This system was used to test letters going through the post office for anthrax. This system was for food testing, and it's about this big, but it was set up with a huge centrifuge so they could test 200 to 300 gallons of water from carcass washes or vegetable washes within 10 minutes and detect E. coli and Shigella and Salmonella and all those other nasties that cause food poisoning. In the course of that study, one of the things we were testing for was the toxin, staph enterotoxin B. We started looking at blood samples to see who had been exposed and discovered everybody who had eaten in the NRL cafeteria had antibodies to staph enterotoxin B, told about the food that the Navy provides. This was used for Washington, D.C. to test for pollutants in the water supply. And this one is put on an underwater vehicle that's run off a little PDA, a little phone-type device that goes around harbors to test for explosives in the harbors. So what do all of these things have in common? They all keep you healthy. They keep you from being blown up. They keep you from dying of food poisoning. But the most exciting one is actually this one. This is a device that is made for testing blood, or a drop of blood for infectious disease. And it's been used in a human trial for over 2,700 people, new mothers in Africa, to test for simultaneous infections of AIDS, hepatitis, and syphilis. And why do they want to? Because the treatment is different if you have one versus two of those diseases. So it has actually been responsible for saving quite a few lives of both mothers and babies. And it's now being used not only for human testing, but they've got a subsidiary company, spin-off company for animal testing. Okay. So if you are going to try to address one of the problems of to improve our healthcare system or any other problem that you see, that you think you can do in engineering to solve a problem, how do you do it? Well, the solution just doesn't appear out of thin air. You have to really assess the problem. You have to understand what is the critical technology that really is important to solving that problem. And don't pick your favorite necessarily, pick the one that you think will work the best. And you really have to think about all of the things that go into it. If you come up with an idea, you want to protect that idea. You do that, the patent process is one way to do that, keeping it a trade secret is another, but don't go overboard. If you try to, it's been my experience that people who work super hard at protecting their idea only have one, okay? So just because you lose one doesn't mean you don't have 10 following it along behind it. The other thing is, any idea that you develop is going, and let's say two people go off and develop the same idea, they're going to develop it different ways. So a good idea will tend to take on a life of its own, and everybody who works on it will add to that product and make it better, and usually in ways that you would not have thought of. So being too protective of your idea is not a good thing. Protecting it with a provisional patent when the time has come is a good idea, but there are a lot of ideas that are probably better off just being. If you don't have the resources or want to take time to market it, let it go. Put it out in the public domain and let it be massaged and worked on, and till somebody can put together a good solution. Our goal here is really to solve the problem, and not. There are lots of ways to do that. I would also say that transitioning to industry can be done in multiple ways. Starting a company is one way, but for most of us who are young, and I'm still young, and have a lot of other interests besides just working, transitioning a company through a patent license is a really good way to get the product out to the market, to get the expertise in the business community and the legal community behind the product, and to bring in the resources for development that you may not have. These products, as I said, they have a life of their own, and it's like having your kid. You give birth to this kid, you bring it up through school, you send it to college, and then it goes off on its own, and it may end up being a very different individual than you expected it to be, and that's not necessarily a bad thing. So if you want to transfer, again, this is pretty much what I just said. There are lots of ways to do it. Advantages the licensing to a pre-existing company is a really good way to get your ideas out onto the market. The other thing is, don't underestimate the value of a good team, and a team that has very diverse talents and skills. Even in the very early design phase of a product, there are plenty of examples where having somebody who thinks differently than you about what's important of that product ends up being very key to its success, whether it's cultural difference, their difference, difference in values, or simply difference in background training. All of those ideas will make a better product. And maybe afterwards we can have some time to discuss some examples of that. Pay attention to time. So these things don't happen overnight. And sometimes it takes a while to even figure out if your idea is patentable, much less feasible. But you have to finish. Keep going till it's finished, or at least your part of it is finished. Don't give up too soon. This is just a roadmap from innovation to a product in my experience. And it also tends to be cyclical. I've talked about a lot of these steps along the way, but many times you do a loop-de-loop around this path. It's not a straight path. And I think I'm running out of time, so I'm going to stop here. This is just examples of my most recent invention and where we are. But one thing I would like to really emphasize is that, remember, no idea is created good. Every idea has to be massaged, bumped, kicked, and knocked into shape before it becomes a good idea. So don't get too in love with your own ideas without taking on all comers. And then proceed towards your goal with the input from all. And enjoy the process. And again, you can't use up creativity. The more you use, the more you have. So I will stop here and take questions.
Thank you. That was a great overview of how engineers can transition their innovative ideas into products that will create real value for society. I hope that all of you in the audience have learned something new about the path from research to products and some exciting innovations in the area of health, and that you're inspired to learn more and take some action in developing innovative solutions to challenges that you're passionate about in the future. For the remainder of the time, we will give you, the audience, the opportunity to ask Dr. Ligler questions about her work, the field, or anything else that you're curious about. If you're joining us live, please submit your questions via text message to the number provided on the program that you got when you entered. If you're watching via live stream, please comment your questions in the chat through YouTube. We'll do our best to answer as many of your questions as possible. While the audience is submitting their questions, we'll go ahead and take a seat, and I'll get started with a few of my own. All right. So when you were talking about different types of biosensors, you mentioned one in particular that you were very excited about or that you thought was like the best. Are there other technologies or tools, beyond your own work or beyond those particular biosensors that you're super excited about or see great potential in for medical or other applications?
Okay, I think the answer is absolutely yes. So all of these biosensors were optical biosensors. And when I first went into the field of optical biosensors, I was told that I'd never make anything portable because if you're not using an electrode, you can't make it small. Well, we know that's not true anymore. We have organic photodiodes and organic light sources. Everything can be made in a very, very small fingerprint. What is I think a future paradigm for biosensors is to take a lot of these integrated optical devices, we're already starting to make them wearable, but we can now, instead of putting a sample into the biosensor to interrogate, we can put a material in the body or in the water that we want to test or in the food and interrogate it with that small optical device. So instead of bringing the sample to the biosensor, we're taking the sensing substance into the place where we want to detect it, and then being able to interrogate that as necessary. And I think that kind of footprint and paradigm is going to allow us to measure what's going on in vivo. I'm very involved now in tissue engineering. I want to look at what's happening as those tissues regenerate in vivo, without obviously cutting off somebody's arm to see if it's working. And the same thing can be done in a whole variety of different formats with much less disturbance without having to extract sample. So I think that is a huge opportunity for biosensor technology to start a whole new mode of operation.
Cool. Very interesting. So there's several different applications that you mentioned or problems that you could solve and that you looked at solving with biosensors. So as an expert in this area, what do you think are the most important or critical health challenges that we face?
I like to think of the health challenges in the broadest sense. So I would say clean air and water are huge. Without those, the impact on human health is just unmeasurable. I mean, if you look at what's going on in India now and China, they're starting to really be aware of the impact of air pollution in a way that is just unprecedented. And we're going to hear an awful lot more about that. If you look at our cities today, for a while they were getting cleaner. Now I think that trend is reversing. As the cities just get bigger and more crowded, they are getting more polluted. Our water supply is getting very tenuous in terms of clean drinking water. I think those are major problems. And the next two would be healthy eating habits, as not just access to nutritious food, but understanding how to eat, how to use good nutrition, and the increased transportation of people around the world is clearly fostering epidemics that are coming from one place to another in an unprecedented manner, and I think that's a huge threat.
So in your talk, you emphasized the importance of understanding many different aspects of the user and design criteria in order to create successful solutions. How does or what are some of the best ways, I guess, that an engineer can use to gain the understanding of the user? Are there specific actions they should take or methods they can use?
Yeah, go be one.
Yeah.
Go be one. So if you want to make something for the clinic, go to that clinic. Talk to the doctors and nurses. Talk to the patients, see what's acceptable. Especially if it's not in a country or a culture that you're familiar with. It's really important to get your own boots on the ground and talk to people and find out where they're coming from. What, as I said, not only what kinds of technology they can tolerate, but also what kind of information will be actionable for them. You know, if they don't have any way to cure a certain disease, well, why do they need to diagnose it? I mean, you know, there's some really practical problems that need to be addressed.
Okay. So the concept of value is an interesting one, which you touched on just a little bit, particularly since our focus as engineers is to develop solutions that create value for people. So you mentioned assessing value, and you had some information up there about different methods or metrics people might think of to assess it, but they're all different. So as an innovator, when you have different people that have different values or different ways that they assess the value of something, how do you balance those different interests? Whose metrics or definition of value do you design for? Probably a hard question, but.
It's not a hard question, it's a bit of a complicated answer. So as an engineer and a designer, I have issues of which I'm passionate about, problems that I care about that I wanted to solve. In terms of design, for me, the value is who will benefit if it works. That's not going to be the kind of value a company is going to look for. They want to be able to make ends meet, to provide a product, and preferably make some profit as well, to be successful as a company. And then there's the value that is to the user. If they can make a decision based on that product that improves their life in terms of sustainability of life or just happiness, well, then that's a value. So I think all of these different tiers of value have to be taken into consideration as early as possible in the design process. You have your sense of value, but you need to think of everybody else's as well.
That's great. So this kind of connects that a little bit in some way, but when developing a new technology, there's obviously lots of technical challenges that you might face in ensuring that you make something that actually works and can be manufactured, among other things. But what other non-technical challenges do you also face in developing a new technology? And do you feel like the most pressing issues are technical or something else, like cultural or political or economic or you name it?
I have seen an awful lot of really good technologies that go nowhere. And part of it is user acceptance. Part of it is the way they're marketed or maintained. I think the technical challenges are the easiest to address for me because I'm a technology-oriented person. If I have a technology problem that I can't solve, then I just go try to find somebody else who can and bring them and motivate them to work with me. I'm not proud. I'll go ask for help from anybody who can help me. I'll tell you a secret too. If you ask somebody for help, they are then invested in your success. So keep that in mind. Don't be shy about asking for help. The hidden problems are the ones that are harder for me. For instance, the device that we made for doing 5 different drugs of abuse and alcohol in 1 minute on a saliva sample worked beautifully. But the company who was making it went belly up because of mismanagement within the company. Okay? That is something, and that's after we got FDA approval. Okay, so it had gone all the way through that level of success, if you will. So for economic reasons or really personality reasons, it went belly up. And by that time, the patent had run out, and we really couldn't find somebody else to make it. So I think those problems are very real. They're just but they're just not problems that I can solve. You do the best you can to try to anticipate the problems and find the best possible partners. And then if it doesn't work, you just move on and go on to the next thing. But that doesn't mean it was a lost effort.
All right. So it looks like we've got some audience questions coming in, but before we move there, just want to ask one more question. So let's talk about why you're here. What inspired you? So what inspired you to get involved in the work that you're doing now, and what motivates you most?
Okay, well, in terms of now, being the last 6 or 7 years since I left the Naval Research Lab, when I decided to retire from NRL and go back to academia, I spent about 3 years first asking myself, what did I want to do with the last part of my career? And I decided if everything works, it takes 10 years at least to go from an idea to a product, that what I would do was try to help other people learn to do that. The thing I was most proud of was not these 11 products, but my postdocs. At that time, I had 50 postdocs, and I did a survey of what they were doing, and I was blown away at what my postdocs had accomplished in all kinds of fields, not just science and engineering. So that's what motivates me now. That's one of the reasons I believe in the Grand Challenge Scholars Program. It talks not only about academic and technical excellence, but how to get your products out through entrepreneurial activities that might be intrapreneurial, how to build a team to get it to the next level. It talks about global participation. We are members of the community of the earth, not just the United States. And I think understanding other cultures and being able to work with other peoples is extremely important. My list of friends certainly circles the globe, and that's been a very rewarding experience. That's the reason. That's the reason I'm here today, is because I really do believe in the Grand Challenge Scholars Program, and I think it builds the kinds of engineers that are really going to make a difference in the long term, and they're you.
Absolutely. Cool. All right, so we'll move on to some audience questions. So the first one is, did you ever feel like there were more challenges for you being a woman in your field?
Oh, yeah. So when my first, I had planned to stay on the academic track, and I was offered 3 tenure track faculty positions at Southwestern Medical School, and the head of internal, by 3 different departments, and the head of internal medicine refused to approve a faculty position for a female PhD as a matter of policy. If I'd had an MD, he would have approved it, or if I'd been a male, he would have approved it, but not a female, because everybody knows they just go have babies, right? So that's one of the main reasons I went to industry. I had not only there, but very negative experiences interviewing for faculty positions. And when I got to industry, it was very clear that they cared a lot more about what I could do than what I looked like. I think obviously it's gotten a lot better.
Yeah.
That guy would have had his pantsuit off now. But I didn't want to give up my career to go on that campaign. So I think it's much better now. But there is one thing that's going on that's kind of interesting. So, okay, keep in mind I was the 3rd female bioengineer elected to the NAE. Frances Arnold, who won the Nobel Prize, was the 2nd. And the first one was is the woman who has the most cited patents in the entire United States. So that's the kind of level you had to achieve. That's not true anymore. You know, there's a lot more parity now. So the flip side of that is we're not as special anymore. So that's not a bad thing, but it also means that, you know, we're pretty much on par with everybody else now.
Cool. So this is a pretty broad question, but we'll see here. How did you come up with the ideas and technology behind the biosensors? Were those your sole ideas, or was there a full team of engineers ideating?
So the first one was the fiber optic sensor. So we put antibodies on a fiber optic sensor, and to make, at that time lasers were like this. You know, we made a fiber optic biosensor that would keep your tent warm at night, right? And the way that happened was another person in the group and I were talking about the problem and what we could do about it. And I said, well, I know how to put the antibodies on. I was trained as a biochemist after all. I know how to do that part, but I don't even know how fiber optics work. And he said, oh, I know that part, and I can do that. And so they explained to me how the fiber optics work, and I explained to him, and I came up with the ideas of how to immobilize antibodies and keep them functional, which people really hadn't done very well at that point. And together we came up with the device. Then from then on, and they taught me enough engineering that from then on, I could start using the general principles to make systems better and better and better. But I never did anything by myself, ever. I've always had helpers, people, or not helpers, peers. In fact, at one point my group got to be about 25 people, and NRL is a soft money research house, so I was spending all of my time writing proposals to keep us funded. And it just got to be too much, so I spun it off. And from then on, I worked with a group. I supported about 7 people, but I would pair up with other individuals when a problem came out to figure out a solution to that problem. So I'd be PI one time, or co-PI the next time, or a worker bee on another project to do whatever was necessary to find the solution and to bring in the right skills and expertise to make it work.
This one's an interesting one. Were there any ideas that you published that you wished you had patented?
Yes. We were working with chitosan, which comes from crab shells, and making these beautiful iridescent layers that would change color when they bound heavy metal. And we could modify them actually to be selective for different heavy metals. And we took it upstream on the Potomac River, actually right near my house, and discovered to our dismay there really was heavy metal still in the water where it was pulling our drinking water out of it. And we confirmed it was there by atomic absorption, thinking we weren't going to find anything. So these sensors worked really well, but the NRL had decided not to patent it at the time. And when the head of the lab, or the director, found out how good these things were, they were written up in the news, but that NRL hadn't patented, he changed the entire patent system to make it less risk averse. Because he really missed one in then. But
Interesting.
I have to tell this story. So one of the things that I do from the National Inventors Hall of Fame is go to Camp Invention. So 200,000 children every summer are involved in Camp Invention. This is an elementary school camp to teach kids how to be inventors. And so in a question and answer session for 7-year-olds, they asked me, what was your favorite invention? And I said, it's one that didn't work. He said, really? I said, yeah. He says, well, what was it? And I said, well, I had taken these beautiful blue chitosan films, and it turns out that look like butterfly wings. They're just gorgeous. But it turns out chitosan also absorbs fat. So I thought if we could put them on M&Ms, you could eat all the M&Ms you wanted and you'd never get fat. We'd sell it to Hershey's and make millions of dollars and fund Camp Invention forever. And so they said, well, why didn't it work? And I said, well, you have to dissolve the chitosan in acid, and when you put the M&Ms in acid, they dissolve too. So this 7-year-old says, well, why didn't you freeze the M&Ms? And another 7-year-old pipes up, yeah, use that smoky stuff. I said, you mean liquid nitrogen? Yeah, that stuff. Why weren't you in my lab? So the good ideas and the solutions to your problems can come from anywhere.
That's great. All right. As a biomedical engineering student, I would like to know, how can I help with these problems? Is joining a company sufficient, or are most companies just focused on one issue?
I don't think anything is sufficient. There are multiple roads. You can solve these problems as an academic, you can solve them in a government lab, you can go into industry, but no matter where you go, you'll focus on one problem for a while, or maybe a couple of problems, but all problems evolve. Let's say you solve the basic problem, well then you've got to develop the next level of the device. Mm-hmm. So there's a whole nother set of development problems that require creative engineering solution, or there's a funding problem, or a marketing problem, or something else, or you move into a different area. One of the things that I did that I think really helped me was I had a conscious policy. Every 5 years, I would look around, and I always read Science and CNE News and some broad journals, as well as the specific ones to my field. I'd look around and I'd say, what is the most exciting thing going on in science and engineering that's just starting? And are there fields, are there areas of that kind of research that I'd like to get into while they're still new? Mm-hmm. And if possible, I would start seed projects in those areas as just kind of on the side. So I don't think anything's ever sufficient. Not if you have a creative mind and an energetic bent. There's always more you can do, there's always more to learn, and nothing you learn is ever wasted. I do a synthetic organic chemistry process once every 17 years, whether I need to or not. Mm-hmm. So, everything you learn is useful at some point, although you may not realize that it will be in the future.
Cool. So what are the advantages and disadvantages of being an inventor in the academic setting as opposed to the private sector?
if you are in a company that has its goals and motivations aligned with yours, then I think you're in a place where you can probably take advantage of your innovations somewhat faster than you can in academia. In academia, you have a chance to make that initial innovation pretty fast, but to do anything with it, you have to go out and get a grant. You still have to teach students, and the resources of the universities for protecting your intellectual property are limited. So they do have to be selective about what patents they file, unless you are fortunate enough to have your own money for filing your patents. It's a good thing to use a chair for, but most of us don't, most of you don't start out having chairs.
Yeah.
So I think I really enjoyed my time in industry. I think I was very frustrated in working for a large company after a while because they weren't taking advantage of my innovations. But I think that would have changed as DuPont broke up into smaller entities. My whole group went to Merck after I left.
All right. As we are getting near the end here, I'd like to end with some sort of a call to action, returning to what you mentioned at the conclusion of your talk about realizing your vision. About the audience realizing their visions. So I'm sure that you've inspired some people here to take action. So what are some first steps that students and others can take to realize their vision and start addressing challenges like some of those that were mentioned today?
Well, your design courses and capstone courses are a great opportunity to pursue something you're passionate about. You usually get some choice in the problems you pursue, and you certainly have plenty of choices in the way you try to find solutions to them. And you have teammates that know things that you don't, presumably. If you can motivate each other to work in the same direction, that's a really good opportunity. There are also opportunities in some of the nonprofits in the area where you can volunteer and in many cases make a real difference. Other opportunities include things like some research in a laboratory or either during the term or during the summer or internships in companies. What I found, I had over about 240 summer students from all over the country working in my lab during the 28 years I was in NRL. And I found several things. It didn't matter where they came from. That where they came from had no bearing on how good they were, okay? So I don't care if they were from Harvard or Caltech or ASU or some little university I'd never heard of. That wasn't really important with how well they worked in the lab and how creative they were. The first year they came, most of them were really involved in learning how to work in the lab and understand the problems we were dealing with and understanding the technologies at their disposal to address those problems. But many, many of them came back for a second or a third summer, and they made very significant contributions to the projects. 2 undergraduates actually had a patent. They put my name on. I said, no, you did this on your own. I took my name off, and they got the patent.
That's awesome.
Just the 2 undergraduates. Of course, they never marketed it, but too bad. It was a good patent. Anyway, so there are lots of opportunities, and you can do many of them before you graduate.
Cool. So that's all the time we have for today's event. Thank you for joining us this afternoon. Our next speaker event will be on January 27th. Please check our website for more information on future events in this speaker series. Audience, please join me in thanking Dr. Ligler again for a great, inspiring talk this afternoon.
Thank you for coming.